Part of determining the molecular shape of a molecule also lets us figure out some of the properties of the molecule. For example, the polarity of a molecule. We need to know the shape to be able to look at each of the bonds, what's the geometry of each of the bonds, and so based on the geometry of the bonds and the polarity of the bonds, is the overall molecule polar or nonpolar. So here's just two examples, carbon dioxide and water. Both carbon dioxide and water have polar bonds. Carbon to oxygen is a polar bond, and oxygen to hydrogen is a polar bond. However, they're not both polar molecules. And that's because of the geometry. Carbon dioxide, if we look at the carbon-oxygen bond, both of those carbon-oxygen bonds, due to the linear geometry of CO2, both of the carbon-oxygen bonds essentially cancel each other out. So we do have a dipole, right, as indicated by this vector, but if we look, both of those dipoles are identical and opposite direction. And so they cancel each other out, and then the overall dipole moment for the molecule would be 0. Whereas if we look at oxygen, oxygen does not have a linear geometry. Oxygen has this bent geometry because there are 4 electron domains in oxygen. It has an electron domain geometry of tetrahedral. 2 of those domains are bonding, giving us this bent geometry. Because of that, if I look at the 2 dipoles now, both of those vectors do not cancel out. Rather, both of those vectors add together to give us an overall dipole moment of the molecule. And if I were to look at oxygen in water, I would notice that there's a partial negative charge on the oxygen because there's extra electron density on oxygen compared to the hydrogens. So I'd have a partial positive charge down here on each of the hydrogens. This imbalance comes because we're looking at a difference in electronegativity. Oxygen is more electronegative than hydrogen, so it's able to pull the electron density in that covalent bond closer to oxygen than it is toward hydrogen. So really quickly, we should review our trends in electronegativity. And so in general, electronegativity increases from the lower left-hand corner to the upper right-hand corner in the periodic table, where fluorine is the most electronegative element. And so to determine if we have a polar bond or a non-polar bond, basically we're looking for something that has a difference in electronegativity to give us a polar bond. And usually, if our difference in electronegativity is less than 0.5, right, our bond would be considered non-polar. And then if we're greater than 0.5 all the way up to 1.9, we'd be considered a polar bond. So a difference of 0 to, 0.5, we'd be nonpolar. Whereas if we had a difference in polarity of 0.5 all the way up to 1.9, we'd be considered a polar bond, and then anything above 1.9 would no longer be covalent, it would be an ionic bond. But essentially, the farther apart we get in the periodic table, the more different would have a electronegativity, and the more polar that bond becomes. So now let's just look at polar bonds and the geometry of a molecule to determine, do we have a polar molecule or not? For the molecule to be polar, you need to have a polar bond, and you need to have a geometry where those polar bonds do not cancel each other out. And so right here, the easiest case, in a linear molecule like HCl, chlorine is more electronegative than hydrogen, so it's pulling electron density away from the hydrogen. I'd have a partial negative charge on the chlorine, a partial positive on the hydrogen. That would be a polar molecule. Those 2 vectors do not cancel out. Whereas if I look down here in the boron trifluoride, I have 3 electron domains. I would be trigonal planar. Each of these electron domains, each of these boron-fluorine bonds are polar, but each of the bonds are pulling equal magnitude, and all 3 directions would cancel each other out because we're on this trigonal planar arrangement. Each of the bonds is approximately 120 degrees apart. So each of these vectors would end up canceling each other out, and then overall, the molecule would be nonpolar. We'd observe the same here for carbon tetrachloride. Tetrahedral geometry, 4 electron domains. I have a carbon-chlorine bond that is polar, but overall, the vectors will cancel out because they're equal magnitude and they're pulling in 4 different directions. However, if I go from carbon tetrachloride and replace 3 of those chlorines with hydrogen, now I would have a polar molecule. Because my carbon-hydrogen bond is nonpolar, now I only have one vector, and that one vector right there between the carbon and chlorine and a one polar bond, there's nothing to cancel out that vector, and now I would have a polar molecule because I'd have an imbalance of electron density across this molecule. The same over here for ammonia. Got my lone pair of electrons on nitrogen, right? Each of these, nitrogen is more electronegative than hydrogen, so each of these bonds, nitrogen is pulling electron density closer to nitrogen, farther from the hydrogen. Each of these vectors, because of the geometry, they do not cancel out, and they would give you a polar molecule. So we need to think about, do I have polar bonds? And if I have polar bonds, what is the geometry of the molecule? Based on the geometry, if those polar bonds cancel each other out, or the vectors from those polar bonds cancel each other out, then I could be nonpolar. If those vectors are cumulative or additive, then I could have a polar molecule. So 2 questions from the homework that discussed this. I have water. So water is a great example of a polar molecule because, again, looking at the geometry, right, it's not linear, it's a bent geometry. Oxygen is more electronegative than hydrogen. So in net, I'm pulling electron density toward the oxygen, and there is an imbalance. I would have a polar molecule. The same down here for the arsenic tetrafluoride, right? If I look at those vectors on the arsenic, these two are 180 degrees apart, so these 2 arsenic-fluorine bonds would cancel each other out. However, if I looked at the 2 equatorial positions, the 2 equatorial arsenic-fluorine bonds, these 2 bonds are 120 degrees apart. There is no vector over here to the left to cancel them out, so I would have a net vector pulling electron density toward the right of this molecule, and as a result, this would be polar. If I look over here, again, I want to see, do these vectors cancel out? And it's important to know the geometry. Here they've drawn the geometry for us, but again, both of those fluorines, 180 degrees apart, those vectors cancel out. Both of these fluorines, 180 degrees apart, those 2 vectors cancel out. Both of these chlorines are 180 degrees apart, and both of those vectors cancel out. Overall, the molecule would be nonpolar. And here, if I had carbon tetrafluoride, if this was symmetrically substituted by 4 fluorines, then it would be a nonpolar molecule because all of those vectors would cancel out. However, this is kind of like the water example where I have 2 polar bonds. The carbon-fluorine bond is a polar bond, so those 2 polar bonds, there's the vector for each of those. The carbon-hydrogen bond is nonpolar. But again, looking at those 2 vectors do not cancel out. They are cumulative, and so the net vector would be somewhere in that direction. And yes, I would have a polar molecule again. So we need to think about each of those bonds that are polar, and then based on that, what are the geometry of the molecule, and do those vectors from polar bonds, do they cancel each other out, or do they add together? The last question from the homework question about this topic, at least question 9.19, very similar. We need to think about the geometry of the molecule and do all of those vectors cancel out. So we'll see here all 4 of the fluorines around the equatorial position would cancel out because all of these fluorines, right, they would have another fluorine 180 degrees apart, so those vectors would cancel, However, this axial fluorine, right, 180 degrees from it, I only have a lone pair of electrons, so there would be nothing to cancel out this vector of the axial fluorine. This molecule would be polar. Here, a trigonal planar, yes, I have a polar aluminum chlorine bond, but each of these 3 vectors are pulling equal magnitude, opposite direction, each of those three vectors would cancel each other out, and overall the molecule would be non-polar. Here, along the axial, fluorines, right, 180 degrees, 180 degrees, they cancel out. My equatorial chlorines, 180 degrees apart, 180 degrees apart, they cancel out. However, if you notice here, we have an unequal substitution pattern. I have chlorine on one side and fluorine on the other side. Fluorine is more electronegative, so if I want to think about the magnitude of that vector would be larger than the magnitude of this vector, and they will not cancel out. And because of that, this would be a polar molecule because fluorine is more electronegative than chlorine, so we'll be pulling electron density a little bit more to the left side of the molecule from the right side. Those vectors do not cancel out. Overall, the molecule will be polar. And then here with the phosphorus hexafluoride, again, we're back to that symmetrical substitution. So all of the vectors, yes, we have a polar phosphorus fluorine bond, but all of those vectors will be 180 degrees apart. They will all cancel out. And overall, the molecule will be nonpolar. So hopefully that helps, but we need to think about the geometry. Think about if I have a polar bond, what is the overall geometry of the molecule and the vector from that polar bond? Is there something to cancel it out, or is it unbalanced in the molecule? And if there's no balance to the molecule with respect to the geometry and the polar bonds, then yes, overall the molecule would be polar.